In 2 minutes? No, in 1 minute, we will start streaming the countdown.
Okay, dokie.
Blow my nose now.
Yeah, it's better. Good evening, afternoon, and probably morning, everyone. Thanks for joining. My name is Anastasia, and I work as System Safety Engineer in DMD Solution. Before we start our webinar dedicated to ARP4754A, I would like to give the floor to Joanna to introduce our company.
Thanks, Anastasia. As you probably know, DMD Solutions is the company organizing this event and all the content of the RAMS Academy.
DMD Solution.
We are an engineering consulting team fully dedicated to the aerospace industry, mostly for design and some maintenance activities. We work for customers who build aircraft, but also rotorcraft, drones, advanced air mobility vehicles, and avionics systems. Our focus has been traditionally in RAMS engineering, but we have been growing a lot lately into systems engineering, and that is why we have also expanded the range of our content for the RAMS Academy. And the reason we are today holding this webinar on the main standard that organizes the work of system engineers for the civil aircraft industry. Anastasia has wide experience in avionics and has participated in several development projects which need certification, which means she is well versed in the practical application of ARP4754 in the industry. So without further ado, I hand over to our speaker today.
Thank you, Joanna. All right, we're ready to start. In the next 15 minutes, we'll delve into ARP4754A, a guideline in civil aircraft and system development. So while the content of this webinar, I would say, is for more junior and mid-level engineers, I believe that the seniors might find it useful as well. Thank you, Joanna. How do we organize our process? So we will have several parts. We will discuss the applicable development guidelines and why we use ARP4754A. We will look at the general development process. Then we will move on to the longest part and discuss each process and its output separately. Then I will provide an example of typical system development process in the form of sequential stage. I'm sure most of our audience knows that a new version has been released, and we will have a few minutes to discuss the main differences between version B and A. And we will wrap up our webinar with a short Q&A session. So let's roll. You are presented with the system hierarchy used in the development of aircraft. At the top is aircraft itself. Then it breaks down into systems. If it's necessary, then an additional subsystem level is allocated. Then comes the equipment level, or we also can call it line replaceable unit level, which in turn breaks down into items. These are hardware and software. The development of each of the levels must be carried out in accordance with its own guidelines. So the aircraft system subsystem equipment level is subject to ARP4754A, software to DO178C, hardware to DO254. The ARP4754A, which we will talk about today, is a document which was developed in the content of the CS25, which is large aircraft. However, it's also applicable for the CS23, 27, 29, VTOL engines and propellers. So the first question that comes to mind is why we use ARP4754A. So for each CS certification specification, the authorities issue an AMCs. These are documents which illustrate means to establish compliance with the CS requirements. For instance, AMC 25.1309 recognized ARP4754A and ARP4761 as an acceptable method for complying with the CS 25.1309, elevating ARP4754A from a guideline to a mandatory status. The figure here outlines the relationship between various development documents, which provide guidelines for safety assessment, aircraft and system development process, which is our today's topic, electronic hardware and software lifecycle processes. On our DMD YouTube channel, you can find a real comprehensive webinar about the ARP4761. If you're interested in watching it, please reach out to us for the next link. Here, I want to emphasize that despite the hierarchical structure that we saw on the previous slide, the links between guidelines are bidirectional, implying both top-down and bottom-up dependencies. So ARP4754A was released in 2010 and ARP4761 in 1996. At the time we were preparing this webinar, the new version were not available, but at the end of December 2023, they were issued as a Christmas present for all system and safety engineers. However, the core of the development process in B version remains the same as in A version, and a lot of current projects under development are still using A version. That's why we decided to keep that webinar, and from time to time during it, I will add some notes about B version, and in the end, I'll sum up all changes about the B version. But let's come back to our A version. So this is a visual depiction of whole development process. This figure can be segmented into 3 parts. These are the planning process, the development process, and the integral process. While the definition of the planning process and development process usually are clear, the definition of integral process sometimes raises questions. So why it's integral? The process is called integral because it continues through the whole project life cycle at each development level present here. So now we are entering to the longest part of our discussion. We will talk about each of the process step by step, and we will start from the planning process. I would say that the planning process consists of 2 parts: brainstorming to determine the plans and contents, and then their formal documentation. We start with the identification of plans we need to release, then we define the development phases and allocate each of the phases to our plans. After that, we establish a clear, that's important, criteria for transition between phases that we defined. Then we establish connection between plans and determine what we will do if the deviation from plan is noticed. And of course, we need to determine which standards we will be guided by when we developing the product. At the next step, it's necessary to document the plans, put them through the review process, approve them, and if everything is in order, then we are ready to move on to the next development stage. So how do we determine which plans we need to release? Table A1 defines this from ARP4754A. As you can see, the need to issue certain plans depends on design assurance level. I believe that the most attenders are aware of it, but if you don't know what metrics it is, that's all right. We will figure it out and determine how to assign DAL to functions or items. So the DAL is a measure of the rigor applied to the development process of aircraft system or items. I want to ask you to be patient, and I promise that we will return to the concept of DAL a little later. For now, let's focus on the fact that the list of plans is determined by DAL metrics which has levels from A to E, where A is the most rigorous level. So we have 7 plans. These are certification, safety program plan, development plan, validation plan, verification plan, configuration management, and process assurance plan. And even for level E, it's necessary to issue at least 1 plan, which is certification plan. Thus, it's impossible to certify a system without any plan. Formally, in ARP4754A, table A1, standards and checklists are not mentioned. For example, in the DO178C, the coding standard is determined as output of the planning phase. However, the necessity, for example, of requirements checklist is hidden in validation process, during which we often use the checklist to prove that requirements are correct and complete. Moreover, having them greatly simplifies the development of systems in large teams. So I encourage you to also release standards and checklists during the planning phase. We have done with the planning process, and let's move to development process. The development life cycle has a beginning and an end and can be re-entered to address aircraft or system changes. The concept stage is a preliminary development stage for research and determination of general aircraft characteristics. When it's ready, it's necessary to develop aircraft functions, allocate these functions to systems, develop system architecture, allocate system requirements to items, and go through the system implementation. The implementation is an act of creating a physical reality from specifications that we defined. In total, from this process, at the output, we have two main documental artifacts. This is the list of aircraft functions and system design description. Let's not forget that at the end of the development process, we also have a physical realization. The aircraft functions are a set of intended aircraft behavior. Usually functions contain verbs like provide, maintain, control, for example, to control aircraft trajectory, or to provide crew situational awareness, or to provide voice communication. Coming back to system design description, which is a comprehensive document that provides detailed information about the design and architecture of the system, its content presented on the slide. A keen observer will note a discrepancy in the output at the aircraft at system level. It seems that at the aircraft level, only functions are required, while at the system level, only architecture is needed. In version B, this part was corrected, and aircraft architecture was also added to the output list. Aircraft architecture is an essential part of the development, and its main input data for the PSAA, which is Preliminary Aircraft Safety Assessment, is always existed before. Thus, the whole set includes aircraft functions and architecture, allocated system functions, and system architecture. Before we go into the next process, I propose to have a look at the whole development process from another angle. The development process also may be represented as a V model. Its core involves a sequential progression of plans, requirements, and products that are baselined and put under configuration management. The left side of V represents the top-down approach, the decomposition of requirements and its validation on each level. The right side of the V represents the bottom-up approach, integration of parts and its verification. Each part of process is carried out by plans that we defined in the planning stage. Now let's progress to the first integral process, safety assessment. Its first place underscores its significance in overall integral process. So the V model of the development process is already familiar to us, and each level is accompanied by its own set of safety analyses. These are functional hazard assessments on aircraft and system level and subsystem level, preliminary safety assessments, common cause analysis, and on equipment level, we usually issue only FMEA. And the final safety assessments, ASA and SSA. The table provides a list of safety analyses that should be released. There is no surprise that the list depends on design assurance level. The ARP4754A requires a safety assessment. The minimum is FHA, which shall be developed even for the DAL E systems. The ARP4754A calls the necessity and the detailed information of how to perform the safety assessment is presented in ARP4761. So the figure here shows the relationship between system and development process. As you can see, there is a constant interaction between the safety assessment and development process. Unfortunately, we don't have time today to go into details. However, there is a free and detailed webinar on the DMD Solutions YouTube channel related to the ARP4761. Please contact us for the link. Unfortunately, a boundary between the safety and development teams is inevitable. The development team follows the system development plan and the safety team to the safety program plan. The different personalities in charge of each of the process. However, the safety and development teams shall be in close and regular contact. Even if you have a subcontractor for the safety assessment, you should meet with the safety team at least weekly to be on the same page, sometimes more frequently if you need an additional technical discussion. Occasionally, I notice some tension between the two teams, but let's remember that the safety and system engineers share a common goal to develop a safety critical system and obtain certification, ideally ensuring company profitability. Unfortunately, the economic landscape requires us also to count money. The next part of our integral process is design assurance level assignment, the metric that we have seen several times, which forces us to issue more outputs. So, the design assurance level is a measure of the rigor applied to the development process of aircraft, systems, or items. There are two types of DAL, functional and item. From its naming, the FDAL is applied for functions and the IDAL for items. The DAL assignment process is a part of the safety process, and it's determined in PSAA and PSSA. Let's consider the terrifically simplified example of DAL assignment. So we start the system safety assessment with the SFHA. Then we consider the function and its possible failure condition and classify failure. It may be catastrophic, hazardous, major, minor, or no safety effect, based on the effect on the aircraft, crew, and occupants. For example, in ATA 34 navigation SFHA, we analyze the function, display attitude information. We classify the loss of attitude information as catastrophic failure condition because under IFAR, instrumental flight rule, for example, fog, the loss of attitude information may lead to complete spatial disorientation and wrong controls input, which potentially may lead to the loss of aircraft. If we work on the CS25 platform, to the function which leads to the catastrophic failure condition, the FDAL-E shall be assigned in PSSA. Then, as part of the PSSA, safety engineer, taking into account the assigned FDAL and system architecture from the system design description, may derive IDAL requirements for software and hardware. In our case, let's imagine that HRS was assigned IDAL-B for PFD, IDAL-A. Thus, the HRS software and hardware shall be developed by IDAL-B and PFD by IDAL-A. The items development is performed in accordance with the DO178C and DO254, but the principles about the DAL is the same. The higher the DAL, the more rigor development process shall be applied. We talked about the DAL allocation process super simply. The thorough consideration of the DAL allocation process with a really comprehensive example is available on our YouTube channel. Now, how does the design assurance level impact the development process? As we saw before, a higher DAL leads to increased outputs from each process. This influence extends to the validation and verification process, where higher DAL requires more methods and independence. Consequently, a higher DAL necessitates completing more objectives, expanding the team size, and increasing the development cost. This complication of development process with DAL increasing leads to reducing the potential number of development errors, which is what we need for highly critical functions. So we have done with the design assignment and moving on. The next part is requirement capture. Usually we distinguish the following types of requirements. Functional, they usually take the largest part of the whole requirement set. They are a combination of customer designs, operational constraints, standards, and implementation realities. The safety requirements. Safety requirements are determined by conducting a safety assessment and then passing to requirement capture process. Additional certification requirements may be required by authorities, and derived requirements, which occupy a special place. Such requirements do not have high-level source. You can't trace them to upper requirements. Usually, they are design or architectural choice. The peculiarity of such requirements is that they must be reviewed from a safety aspect point of view to assess their impact on safety objectives. Therefore, not only systems, but safety engineers are involved in the process of validating such requirements. The output of this process is requirement data. Usually, requirements are stored in requirements management system. For example, DOORS, JIRA, JAMA. Each requirement must be accompanied by its own set of attributes. These are ID, statement, is it assumption or not, and so on. We have published a list of necessary attributes on our website where you can familiarize yourself with it. After requirements are established, we can start the requirement validation process. So validation is the determination that requirements for a product are correct and complete, and the process answers the question, are we building the right aircraft, system, or item? Several methods may be needed to support validation. These methods may include traceability, which is recorded relationship established between two or more elements. In the System Requirement Management tool, we create a link between current and upper-level requirements. If this connection is not presented, then it means that requirement is derived. The connection between elements are usually stored in trace matrix, which is an attachment to the requirement data. The another method is review, which is an application of the personal experience through review, inspection, or demonstration that can support the determination that requirements are correct and complete. Analysis, for example, safety-related analysis, FHA, PSSA. Similarity allows validation of a requirement by comparison to the requirement of similar certified system, and also it may be modeling or test. The required methods of validation depends on assigned DAL. For example, for DAL C, it's enough to use three methods: traceability, requirements rational for derived requirements, and one more from the list. For A and B, it should be at least 4. In addition to A and B levels, the independence should apply. There are two outputs of the validation process: the validation matrix with validation status, is requirement validated or not, and the validation summary. B version of ARP4754 gives us more flexibility in required validation method. Traceability and engineering review are primary methods for all DALs. Additional methods like analysis, modeling, or testing may be optional and uses if traceability and engineering review are insufficient. For example, if a requirement involves a complex state machine, modeling may be utilized. I want to pay your attention to how to check that requirements are correct and complete. To do that, we usually include a checklist, which consists of a list of questions. How to build a checklist? There can be two ways. The first one, I would say, the way of samurai, to build it by yourself, based on the objectives from ARP4754A and proposed question from ARP4754A. I duplicated it here. Then you can supplement it with your engineering experience. And another way is to buy them. Some companies may provide you not only with necessary checklists, but also with plans and standard templates. I think that the advantages and disadvantages of both methods are obvious. I also think that there is a good practice when at the end of the project or at the phase, after the lesson learned, you update the checklist to reuse it in the next project. Thus, the checklists are constantly updated and evolve, and when a new project is kicked off, you can use the updated checklist. Here is simplified version of the validation matrix of multifunctional display requirements. It's simplified because it doesn't include all necessary columns. For example, associated FDAL, required validation methods, evidence, owner of requirements, etc. We will not need it because I want to shake you up a little bit and give a rest from my long speech. I invite you to validate the presented requirements only for correctness. So how we will do that? I will validate for correctness the first requirement, then I'll give you 1 minute to skim them and validate them by yourself, or you can grab a coffee. After that, we will check it. So I'm starting. Let's look at the first requirement. I check its ID, great, it exists, it's unique for current moment. Then I check the trace type and I understand that requirement is refined from a higher level. There is a link and there is a source. I look at the statement. The MFD shall start up within 5 minutes at the temperature between -55 Celsius degrees to 15 Celsius degrees. And I ask question from the correctness checklist, which is now in my head. Are there any conflict with other? No. Can we meet it? My experience says me yes. Is it verifiable? Yes. Is it necessary? Yes. Should I split it? No, etc. So the bottom line, within the set we have, the requirement is correct. Now, I'll give you 1 minute to check other requirements, and then we will discuss each of them. So the time has started. "30 minutes passed. All right, time is over. Let's continue. Second requirement, ID, the same as the previous. The first mistake is derived, but it doesn't have any rational. The second mistake, the statement itself, I would say, is well expressed. By considering the ID and missing rational, the requirement is incorrect and shall be reworked. All right, the third requirement, second requirement, correct, trace type, or correct statement. We have two physical different characteristics combined in one requirement. Thus, it's better to split them. Should be reworked. Fourth requirement, ID, correct, trace type, source, correct, statement, too vague, is not verifiable, should be reworked. Fifth requirement, ID, correct, trace type, source, standard, correct, statement, achievable, verifiable, necessary, correct. Sixth requirement, ID, correct. However, the statement conflicts with another requirement about weight, should be reworked. Seventh and eighth are correct. I hope now you are awake a little bit and we are ready to move on. So let's focus on the verification process because it's common to hear the V and V process. Let's talk about the second V. So verification is the evaluation of an implementation of requirements to determine that they have been met. The process answers the question, did we build the aircraft system function item right? As it was for validation, several methods may be required for verification process. It may be inspection or review, which consists of visual examination of drawings, documents, hardware, software to verify that requirements have been met. An analysis provides evidence of compliance by performing a detailed examination or of system or item. It also may be service experience, modeling, and the most common test or demonstration. So testing, that's critical, provides repeatable evidence that requirements are satisfied by exercising a system or an item. The required methods of verification depends on assigned design assurance level. In addition, for DAL A, all requirements should be verified by independent person. For DAL B, only safety should be verified by independent person. The output of verification process are verification procedure, metrics, summary, and problem reports. Again, B version of ARP4754 gives us more flexibility in required verification methods. Testing is the primary method. Supplementary method may be employed in conjunction with testing or as an alternative, if necessary or applicable. The next process in our integral part is configuration management. There are four main activities of configuration management. There is one more, which is establishing a configuration management plan, but we have already discussed this in the planning process. So the first one is configuration identification. The objective is to unambiguously and uniquely label each configuration item. So what's a configuration item? Configuration item is aircraft system item and related data that is under configuration control. We have already discussed the outputs of each of the process, plans, requirements, etc. And all of these documents are configuration items. But product is not only the related document, but it also includes software with its source and binary code, hardware with physical components, and even set of tools which were used during development. All these mentioned parts are also configuration management items. All of them shall be identified. The second one is baseline establishment, which objective is to create and maintain control of traceability of configuration items. The third piece is archive and retrieval, which objective is obvious to ensure that configuration item can be retrieved. The configuration management engineer shall establish tools where data will be stored, the security rules, the backup rules, etc. And the last piece of our mosaic is change control and problem reporting. The rules of how to perform change control and problem reporting shall be clearly identified. The output of these processes are presented on the slide. Moving forward, the next process is process assurance. There are three main objectives: to ensure the necessary plans are developed and then maintained, to ensure development activities and processes are conducted in accordance with those plans, to establish evidence that the activities and processes adhere to the plans. The output of the process is evidence of process assurance. These are approved plans, reviews required by plans, and confirmation of audits process, audit reports, and checklists. Please do not confuse the role of QA in aviation sector and in the IT sector. In IT, QA is responsible for system verification, which is testing. In our field, QA is about processes. The QA's job is to make sure that we follow the correct process in development, and he or she is usually not involved in technical issues. This is a very critical role, and please do not underestimate it. In my opinion, only the best of the best become QA engineers. The last process is certification and regulation coordination. The certification process objective is to prove that the aircraft and its system comply with applicable requirements. This is the list of possible certification data that should be submitted to authorities. The first contact with authorities should be as early as possible, since ARP4754A states that the plan should be reviewed by authorities before development activities occur. In the B version, the certification and regulation authority coordination process has been eliminated from the integral process. However, this doesn't signify its absolutely absence. Rather, the certification authority coordination chapter has been integrated into the development planning. So, we have discussed all the development processes with the ARP4754A, and I hope that the most of the material was clear. We didn't go too deep into details of each of the process, but we definitely discussed the basis of each of them. However, before we finish, I would rather like to touch one more topic. I propose to place the system on the system without aircraft development process in the form of sequential stages and look at the artifact of each stage again. I distinguish 8 stages of development. The transition between stages is accomplished through the stage review. They are marked with diamonds. The name of stage reviews are not defined in ARP4754A and came to us from military sphere. However, they are widely used in civil aviation development. I would like to draw your attention to the fact that since they are not standardized, they can vary greatly from project to project. I have marked the most frequently used names in my opinion. So the first phase is initiation phase. The stage is highlighted in gray because the artifacts of this stage are not part of the ARP4754A. However, the stage exists, and usually the project manager is responsible for outputs from this stage, such as project description, project management plan, or for some examples, some financial metrics are calculated on this stage. The transition between the initiation phase and the planning phase occurs through the kickoff meeting, where the project resources, deadlines are discussed in general terms. The next stage is the planning phase. during which the plans that we discussed earlier should be developed. If the plans have been reviewed and approved by QA, we are ready for planning review. Here, I would like to talk a little more in detail about how the stage review happens. When documents are ready for stage review, QA or system engineer call a stage review meeting. It's an official request to attend the stage review. The reviewers review artifacts, and then during the official meeting, all issues are discussed and recorded in stage review report. Usually, we use 3 status as a conclusion of stage review. If the status is red, it means that the critical issues were found and they have to be resolved before entering the next stage. The stage review shall be redone again. If status is yellow, it indicates that some major issues were found, they shall be resolved. However, usually system engineers are allowed to continue work on the next stage. An additional stage review shall be called before the next stage review. If the status is green, there are either no issue were found or only minor remarks were raised. An additional stage review is not needed. The closing of all these remarks can be checked during the next stage review. Let's come back to our stages. We ended with the planning review. The next stage is the requirement phase, where the objective is to develop the requirements and validate them. The stage review is System Requirements Review, SRR. The following phase is the design phase. During the stage, we need to establish a design that meets the requirements. In the design phase, usually we have stage reviews, PDR and CDR, preliminary design review and critical design review. The differences between these reviews is level of confidence and details in the design. After the CDR, the design must be fixed because we are entering to the next phase, which is implementation and integration. At this stage, the physical reality is created and assembled. During this stage, the system verificator develops a test procedure and may do unofficial test runs. The stage ends with the TRR, which is Test Readiness Review. The next stage is an official verification stage, usually the most expensive one. The stage review is TRAR, Test Readiness Acceptance Review. The last stage is the final one, which is the certification phase, and end of it is certification review. There are also several stage review indicated on the diagram. It's FRR, Flight Readiness Review, and PTR, Product Transition Review. There may be other stages that you need in your project. Do not forget to indicate all of them in the development plan and establish a clear criteria for the transition between different phases. As I promised, let's have a few moments to compare the main differences between A and B version of the ARP4754. ARP4754B primarily focuses on aligning with the recently released of ARP4761A, meaning there are no supercritical changes in development principle compared to version A. But there are some ones. Here, I highlighted the key differences that I've noted. The first one, the detailed FDAL IDAL allocation content was moved from the ARP4754A to the ARP4761A. Appendix E, which introduces an example of wheel brake system development, was added. This is a great example of collaboration between development and safety assessments. This is a must to read for everybody. 2 new safety assessment techniques were added. There are model-based safety analysis and cascading effect analysis. Required validation and verification methods were updated as well, providing us more flexibility in method selection as we discussed. The section of modification to aircraft or system underwent revisions. We didn't cover this section today, but if you are involved in this process, please review it carefully. And lastly, I would say that there is a special emphasis on unintended behavior in ARP4754B, replacing the previous term unintended function. All right, in closing, before Q&A, I want to say thank you for your participation and hope you found this webinar valuable. It's important to note that the information that I shared here is based on my experience and may differ from yours. I'm always open to further discussion. Please find me on LinkedIn and we can chat if you want. Furthermore, I want to extend a big thanks to engineers from the working group behind the new versions of ARP4754B and ARP4761A who keep the development process updated. As well as I want to thank my current and past colleagues, some of whom may be attending this webinar today. And Joanna, would you like to add something before we go into short Q&A session?
Yes, absolutely. Anastasia, thank you very much for your detailed and on-point explanations on ARP4754. I think the content is amazing. I really like the part when you have us validate the requirements, challenging and thought-provoking. I think we may have some questions. They are not content related. Actually, they are asking if there is a recording of these sessions. This session will be available on our LinkedIn company page. So you can subscribe if you want to be up to date on further content and also to see this webinar replayed. We can also make available the presentation for this webinar if you want to have it in written form. So just please message us through our company page and we can send it to your email. Also, I wanted to call the audience attention on the future content that we are going to publish soon. We will have an extensive piece from Anastasia herself on the modifications introduced by version B of the ARP4754 standard. I think this is very relevant to everyone here today, so hopefully you are up to date when we publish it. Also, and very importantly, related, ARP4761 has also been updated to version A with very important changes that will highly impact the whole industry in the following years, and especially the RAMS engineering teams. So we will be providing content on those modifications in the following weeks and months because there's a lot to comment. And we will divide it in specific subjects such as model-based safety assessment, modifications in common cause analysis hierarchies, interdependence, coffee table, among others. So please keep in touch. And besides from the LinkedIn page, you can also follow, get subscribed to the RAMS Academy newsletter via email, so you'll receive the content on your inbox. We have a low periodicity, so it's not annoying spam. I don't know, Anastasia, if you want to add something else?
I don't see any questions, but that's all right. If you guys need anything, please reach us out via LinkedIn page. If you have some questions about the presentation as well, we will try to answer it personally. Thanks again for your time and have a nice evening. Bye-bye, everybody.
It was a pleasure having you out here today. Thanks for your attendance and hope to see you soon.
Thank you. Bye-bye.